This video gives some examples of proof by contradiction. A proof by contradiction of the statement C assumes not C and proves a statement of the form R and not R for some proposition R. This works because R and not R is always false. It's a contradiction. So we're proving that not C implies false, or equivalently, that not false implies C by taking the contrapositive. Well, that's the same thing as saying that true implies C, and so C has to be true. Before we start proving things by contradiction, I need to mention a few facts. The first fact is that a rational number can be written as a ratio p over q for some integers p and q, with q not equal to 0. So far, that's the definition of rational number, but I'm going to add another bit. We can actually choose those integers so that p and q have no common factors. In other words, we can write the rational number in lowest terms. Another fact that we'll need is that if p is a prime number and it divides a product of two integers, x times y, then either p divides x or p divides y. By the way, this is not always true if p is not a prime number. For example, 4 divides 6 times 10, which is 60, but 4 does not divide 6, and 4 does not divide 10. We're going to need these two facts for the next proof, but we won't prove these facts themselves until possibly later in the class. For our first proof by contradiction, we're going to look at a variant of a classic proof. We're going to prove that the square root of 5 is irrational. So we're going to assume the opposite. We're going to assume the square root of 5 is rational. This means that the square root of 5 can be written as a ratio p over q, where p and q are integers with no common factors, and q is not equal to 0. Let's rewrite this equation as the square root of 5 times q is equal to p, and let's square both sides. That gives us that the square root of 5 squared times q squared equals p squared, so 5 times q squared equals p squared. So 5 divides p squared, which is p times p, and by the fact we mentioned earlier, if 5, which is our prime, divides a product of two integers, then it must divide one integer or the other. In this case, the two integers are the same, so 5 has to divide p. So we can write p as 5 times a for some integer a. Going back to this equation here, we can substitute in 5a for p and get that 5q squared is 5a quantity squared, which means that 5q squared is 25 times a squared. Dividing both sides by 5, we get that q squared is 5a squared, and that means that 5 divides q squared, so as before, 5 divides q. But now we know that 5 divides p and 5 divides q, so p and q share a common factor of 5. This contradicts the fact that p and q are integers with no common factors. We have our contradiction, which I'll write with two arrows butting up against each other, and this completes the proof. We assumed the opposite of what we wanted to prove, we got a contradiction, and so we've proved the statement that square root of 5 is irrational. As our second example, let's prove that among the 435 representatives in the House of Representatives, there must be at least 2 who share the same birthday. Again, we'll do a proof by contradiction. So we'll assume that there are no birthdays in common. That means that we must have 435 distinct birthdays, but there are only 365 days in the year, 366 if you consider a leap year. So there are actually at most 366 distinct birthdays. This is the contradiction that proves the statement. I guess technically, if this is the statement R, then we don't quite have the statement not R yet. The statement not R would be there are more than 366 distinct birthdays. But since that follows immediately from the fact that there are 435 distinct birthdays, we can consider it a complete proof if we stop right here. This video gave two examples of proof by contradiction, where we assume the negation of what we want to prove, and then we prove a contradiction.